All right, good morning. On my way out here yesterday, I told my daughter I'd be giving a talk at 5 a.m., and she says, that's going to be a really terrible talk because you're not a morning person. So my main goal is to prove her wrong this morning. So yes, I'm providing a talk not on causality, but on the backdrop of big data, raising some issues having to do with big data. So if you haven't been working in the area, you might just think, what's the big deal? It's just bigger. And in fact, if you go to conferences on big data, you might be excused of thinking it's just a problem of building bigger computer systems and faster systems and treating data. It's a database problem. I think you can tell by the title that's not my perspective. I think it's an integrated inference and computer science problem. And in fact, it's a deeper integration than anything we've really seen before. It's the first time the fields are really being forced together at their foundations. All right, so let me see if I can figure out. Those goes forward. There we go. Okay, so now let's go back maybe 10 or 15 years. Where did this set of issues start to arise? For me, at least, it was first in science. So the Higgs boson was an example. Science in confirmatory mode. So you gathered a large amount of data to decide whether there was a Higgs boson or not. Statistically, it was just hypothesis testing. There was a little 2x2 table, Higgs boson or not, type 1 error, type 2 error. The challenge, however, was just the huge number of nuisance variables, all the little blips in density curves, all the particles, the billions and billions of extra information that you had to get rid of to focus on the hypothesis of interest. And that created, about a decade's worth of work in basically simulation-based statistical inference. Then the next sort of wave, at least from my perspective, was astronomy, genomics, and the more exploratory fields, not looking to confirm old hypotheses, but rather to find new things, new phenomena in nature, and suggest the next wave of science. So here, statistically, we're in a very, very different world. We're looking at hypothesis spaces, which are massive, exponential in the number of data in many, many situations, and hoping to find cool things. Of course, we find all sorts of things, most of which are just white noise, and the statistical problem is to control all the multiplicity. So that lives with us to this day. That, to me, is one of the big scientific problems of our age. How to make sure that the world is not full of white noise in the media, in medicine, and et cetera, all areas of human inquiry. Now, that wouldn't be such a big problem if it didn't also bring in the computational side. And there, I think you started to see it more clearly when you looked at technology, the internet, measuring human activity, generating the kind of data sets we're seeing to be used for personalization and creating markets and so on and so forth. To me, what was really interesting about this was the granularity. That in the last 10 years, we've seen data sets that are about every single human being and every human's activities. In the past, it was about aggregates. It's no longer about aggregates. So I have the word in the next little phrase here, compound loss functions. Companies' business model is to serve every single human being well. If you don't serve 5% of the humans well, your company will fail. So that's a compound loss function where it's really, really critical to get every term in the sum handled correctly. Heterogeneity becomes hugely important, unknown sampling frames and so on. So now the inferential issues are really, really getting to be front and center. If you build a company just based on taking data and processing it, you will run into all these issues and probably fail if you don't address them well. So that's kind of the statistical emphasis. Of course, there is the computational side. You do have to build the systems and all, but I think it's really actually much more deep than that. And so to kind of dig into that a little bit, let's consider the following job description. So your boss, you've just joined a West Coast startup, prepared to make lots of money. Boss says on the first day, I want a big data system, whatever that means, that will replace our classic service with a personalized service. So maybe a search service, maybe a recommendation service or whatever. I want it to be personalized now because I have data about all individuals. And so you scratch your head and we'll start working on that. And boss adds, I want it to work reasonably well for everyone and anyone. Even if you haven't collected any data about a particular individual, the first day they come in, you should serve them well because they're like other people, right? It shouldn't be that hard to give them a good service. And of course, there's billions of people, so you've got to kind of worry about the hierarchical model or whatever behind this. I can tolerate a few errors, but not too many dumb ones will embarrass us. So now you have long tail issues you've got to worry about and embarrassment. And here's the worst part. I want it to run just as fast as our classic service. Everything up until now is something a good statistician might be able to kind of start to handle. But now suddenly the statistician's out of the room, not out of his or her water. Because in statistics, you never talk about runtime. Okay, you talk about it loosely, but it's not part of the formal theory. It's not part of the training. It's not part of the way you think. So you're prepared just to build a system that will run a certain amount of time and eventually spit out an answer, but you're not prepared to say, well, in 5 milliseconds, I can guarantee you'll get an answer with a certain accuracy as a function of the data, the dimension of the space, and so on and so forth. There are no such equations that exist. So now we're really into the kind of fundamental issues. Now here's the other part of that, which is that it should be as fast as our classic service, but as the years wind on, I'm going to get more and more data, huge amounts of data, and the system should never slow down. Because I'm just giving you more of your resource, you should be happier and happier as I give you more data. So it shouldn't get worse on any dimension. All right? Because in computer science, if I give you more cycles, you're happier. If I give you more memory, you're happier. Suddenly this new resource, to computer science at least, of data, if I give you more of it, things get worse. You slow down. So how do we both quantify that but also not have that happen? That is a fundamental problem that hasn't been faced yet, and I think it's for the coming generations to face it. And now there's all the sort of externalities, other issues that come into play, privacy being one, that also make this problem coupled in a complicated way. Okay, so hopefully that job description gives you some idea of my perspective on why this is the big problem of the era. Big data is not a fad. It's not just for the companies to build systems. This is a core intellectual academic exercise. And I haven't even said the word causality yet, right? But I hope you appreciate that this kind of plays the background of everything. You know, you think about causality, you think about the algorithms for causality. They have to run in a certain amount of time. They involve matching. They involve errors. There's inferential issues and all those things, and so you have to face them in this bigger context. So again, to continue to emphasize this, statistics and computation could have gotten blended for lots of reasons. They haven't really over the last 100 years, even though I think originally Kolmogorov and Turing and so on really thought of them as blended fields. They separated, and they really haven't been together, but now they're being brought together, and big data to me is the driver. The problem is that if you look at core statistical theory, by which I mean statistical decision theory, it has all kinds of dimensions of problems in it, but it doesn't have a role for runtime. You'll talk about the number of data points as a surrogate for runtime, but of course if you're a computer scientist, you know that number of data points is like n, and there's all these other formulas like n log n or n squared or n cubed talking about runtime. So it's not in statistics to talk about runtime. If you look on the computer science side, you have all kinds of equations involving runtime. That's the core quantity, but you don't have statistical risk. You optimize other quantities that are often more ad hoc, geometric quantities or optimization quantities. All right, so we have a fundamental oil and water problem. To make this even more blunt, a computer scientist will often solve a problem by saying, I've got the problem, here it is, I've made a formal structure, and I get an algorithm that runs in polynomial time. Done. Closed. Problem closed. That's just no good for the modern world. We have to be not just n log n, but n and sublinear. That's kind of the world we need to live in to have any hope that we'll build engineering systems that will work in the real world. You know, polynomial time in this kind of world just is that you haven't even touched the problem yet. On the statistical side, often I'm both of these, by the way, we'll say I've solved the problem once I've shown that some procedure is consistent or it's asymptotically efficient or whatever. I have to probably make a lot of IID assumptions to prove such a thing, but the problem is viewed as closed once you prove sort of thing. And that's just not going to cut it either. IID assumptions are just not the way to think about big data. They're very heterogeneous. Okay, so is there hope? Well, first of all, computer science has focused too much on exact solutions or what are called approximation ratios. Those are worst case quantities. And you don't need such exactitude in inference problems. You sort of need 1 over square root of n. So machine learning people, sort of the part of computer science that does focus on statistical inference, appreciates these issues, but they don't really quantify. You need notions of confidentials. Machine learning systems tend to take in an input and give out a point prediction. They don't worry enough about the actual error bar, which will allow you to have a less worst case kind of theory. So we'll talk a little bit about that. The other reason for hope is that laws of large numbers and concentration theorems, which are usually studied to analyze algorithms, can be used in design. If you have a concentration of some kind, you don't have to compute. You know by the math that you're going to be in a certain range, and you just plug in that answer. So this is not very widely appreciated, but I think is going to be part of our future. And then, of course, the word parallel comes up every generation, and it's certainly coming up in ours. Now, again, we're in the statistical world, not just in the classical matrix inversion world. So there's lots of hope here. First of all, there's lots of sampling-based inference in statistics that naturally parallelizes. If you have heterogeneity, you need to do divide and conquer at some level to do the right statistical inference, and that leads to parallelization. And then all the fast stochastic gradient descent procedures are very parallel, and they're helping drive inference and computation relationships. Okay, so I'm going to turn now to a few vignettes that I've been working on this now for about 10 years and have a whole bunch of little pieces of work, and I'm going to give them as examples of what I would mean by a joint statistics and computer science enterprise, equations that really relate the field. So many of them are unified by the following slide, which is that the one general approach that we found has been very productive. Has to be first and foremost statisticians, to focus on statistical decision theory. We're going to guarantee a certain error in statistical sense, and we're going to hold on to that. All right? And then we're going to work really hard to get the computational resources under control. Again, to kind of slightly over-exaggerate, but the machine learning field has often said, no, we're going to worry about just make the system and build it and make it fast, and then hope the error rate will be good. And show it's better than last year's error rate and make the error rate go down over time. So we're going to kind of make that, no, we're going to make that a hard constraint. You got to control the error rate in an a priori or a posteriori way, and then add in computation as an external constraint. So if you do this, this is going to partly be a theoretical exercise, you will induce trade-offs among all these quantities that are both on the statistical side and on the computation side and get equations that link them. So I'm going to give examples of that. Here's the little vignettes. They will go by fast. The main point is not all the details, but just to kind of give you the kind of the work they are. These are in some sense thought experiments. And there they are. So involving several kinds of constraints and then talking a little bit about sampling, which I think is very relevant to causality as well as the other kinds of big data problems. So I'll just also show you some of the names of my colleagues, all people who've been at Berkeley with me. So let's start with privacy. This gets a little bit further far afield, but it's such a nice example, and it is certainly relevant to big data that I'm going to go over it briefly. So just one slide of background. I know there's a lot of econometricians in the audience as well as statisticians. Both of us view Wald as our kind of predecessor. Wald is an amazing guy, foundations of both fields. So statistical decision theory, Wald in the 1930s. Said, look, let's think about estimation and inference and hypothesis testing problems in a unified framework. There's an unknown family of probability distributions. It could be everything. It could be non-parametric. For every distribution P in that family, there is a functional theta of P which describes the distribution in some way. You can call it a parameter. It doesn't have to be classically parametric. You would like to infer that theta of P. You'd like to figure out what theta of P is even though you know what P is. So you have an estimator, which is hopefully close to theta and P in some sense, and you measure closeness by a loss function. Okay? So most statisticians would agree this is a reasonable starting point, and now things diverge. You become a Bayesian or a frequentist, depending on whether theta hat is random or whether theta of P is random. So we're going to be frequentists for most of this talk, and theta hat will be random, as it was for Wald. And so Wald took an expectation over that loss function, where the expectation is over the random theta hat. And got an object now which is a function of P. You don't know P, so it's a function of P. This is before you've seen data. It's just it's called the risk function. So Wald said, it's a function of P. I can't compare two functions of P readily, so let's look at the worst case. Let's take the supremum over all P and get a single number now for each theta hat, and that will be the worst case risk. So this lives to this day, after nearly 100 years. It's criticizable and all that, but it is, as a theoretician, it's a very, very good way to make progress, and we're going to be doing some mini-max in this little section. All right, so in particular, we're going to bring mini-max, Wald-style decision theory, into contact with privacy. So you don't have to elaborate this too much, but privacy's got to be a knob that one can turn. It's not a cryptographic construct. It's something that I might be willing to give you my data depending on the loss function. So if you want to measure my genome, and the loss function involves studying some disease that runs in my family, then sure, I'm going to turn the privacy knob all the way up. If you want my genome so you can show me advertisements, then no, I'm going to turn the privacy knob all the way down. And I want to have control over that depending on the inferential problem. All right? There is a knob that exists out there in sort of the theoretical computer science community called differential privacy. We have borrowed that and put that to statistical purposes. So it's going to be a knob we can turn, and we'll look at how good we're doing in terms of a statistical risk. So that's not generally what's been done with differential privacy, but that's what our little game is going to be here. All right, so here's a little model, which is that data is being collected, x1 through xn. There is a privacy barrier. Those people who hold the data don't want to give it to the central statistician, theta hat, at Google. So they're going in some ways fuzz up the data or masquerade via a channel Q that maps X to Z, and the statistician gets to see Z. All right, and still we now still want to do good inference even though the data have been messed up, and so we don't want to quantify that. So we can have a knob that tells us how messy the data have become via the channel Q and trade that off against the inferential risk. Okay. All right, so there's our setup. Let me slowly move on here. Click, click, click. Okay. I was afraid of this. PowerPoint is messing up on this particular computer they're using at the National Academy of Sciences. My Berkeley laptop would have not done this. All right, anyway. Here is the definition that has emerged from the privacy community. It's a statistical definition at some level. It's a likelihood ratio. You look at the channel. It's a function of the channel, not of the data, not of the analysis of the loss function, none of that. It's just about the channel. It says if the channel is such that if I look at one database X and another database X prime, which might be X is me in the data and X prime is the same database with me not in the data, that if you look at any event S, the sigma algebra on which Q is defined, so adversary chooses S to be an event they can try to detect me in the data or not, that ratio between the two outputs of the channel is not going to differ very much. And that's true over all pairs of databases X and then over all events that the adversary can choose S. Now we have a knob on the right-hand side, which is alpha. If I turn that to be really, really small, I'm really insisting that the distributions be very, very close for all X and X prime. I'm being very stringent on my privacy. And if alpha is big, then I'm not being so stringent about my privacy. All right, so there's kind of a little picture there. It really is a likelihood ratio bound. So now we want to bring that into statistics and put that in the context of a loss function. This is not actually what's typically done. Just briefly, in the privacy literature, what they typically do is take a given database and think about queries they could make on the database. Say, bank accounts and what's the maximal income in the bank or maximal account size. And now you want to fuzz up the database and still answer the query which is within some epsilon of what you would have gotten on the original data. That's not an inferential problem. An inferential problem is here's some data, and I'm going to get a brand new person who wasn't in that data and ask a query about them and use the data there to answer the query about them. And I want to still give a good answer for that new person, even though I fuzzed up the data in the database to protect the people in the database. That's inferential and privacy. Okay, drat. Okay, so, all right, I hope you don't mind that the symbols have kind of slid over onto the text there. All right, so here's the formulation that we've gone. This is a big, long mathematical equation. Let me just sort of unpack it. So on the right-hand side there, you have the supremum over P of that expectation. That's the same thing as before. That was what Wald defined. That was the maximal risk. And then the next thing Wald did says is to pick the procedure theta hat, which minimizes the maximal risk. That's the blue part. You pick the best procedure under this maximal risk. That's called minimax. And now the mathematical problem is to do that for large numbers of problems, regression and density estimation and so on. And the whole right-hand side becomes a number, which is a function of the dimension of the problem, the number of data points n. It goes down as a function of n, it goes up as a function of d, and so on and so forth. And get equations that relate these things. All right, the new part now is going to be this new channel, which is an externality on the risk. We're going to say, well, the statistician theta hat can't look at x. He or she can only look at z. So that's now argument now of theta hat. And now we're going to take the best channel. So we're going to design our privacy mechanism to make the minimax risk as favorable as possible. Okay, so a saddle point problem. So I get to choose alpha and then choose the best channel that does protect me at privacy level alpha, such that I do solve the statistical problem as well as possible. I get a good risk under this well-chosen channel. So that couples everything together. And now the question is, can you do mathematics with this? On that whole thing on the right-hand side is a function of various constants, the sample size, the dimension, and all the usual statistical constants, and it's now a function of alpha as well. And do you get an equation that relates these things? So let me just make this really concrete to help fix ideas. So let's suppose that people have been coming into hospitals and they abuse various substances. This particular person abuses alcohol and cocaine, and not others. And there is in the underlying population, there's a set of proportions of abuse of these various substances given on the right over there. So from data on the left, I'd like to estimate the proportions on the right. Well, if I gave you that data, you'd do maximum likelihood. You'd find the sample proportions or something else. and those would be your estimates. But I'm not going to give you the data on the left because that's private. All right, so is there, what am I going to do? Well, I'm going to fuzz up the data on the left somehow and give you the fuzzed up data so that I protect myself, but I hope you can still do estimation. All right, so, oh boy, this is really a shame. Anyway, we're going to estimate the mean, theta hat, which is our parameter. It's a d-dimensional vector, and we're going to measure errors in some loss function, the L infinity norm, and we're going to do this non-parametrically over all distributions supported on a compact set. All right, so the classical, boy, I'm sorry about, right? All right, so I had to skip over the classical rate. The classical rate has square root of log d divided by square root of n in it. If you just do classical minimax, 100-year-old results, you find this goes as 1 over the square root of n. Because it's a non-parametric problem, that's kind of how the risk depends on n, kind of drives a lot of statistics. And it has log d in the numerator. When you do this in this new setting where we've introduced this alpha parameter as well, alpha does appear in the equation on the right-hand side. And so the sample size went from n to n alpha squared, and there's a new factor of d that appears in the numerator. All right, so the effective sample size now has dimension dependence in it, and it has privacy dependence in it. We've written a bunch of papers doing this. This is with John Ducci and Martin Wainwright. And for all those statistical problems there, it turns out the effective sample size reduction what does incorporate alpha in exactly that way. N goes to n alpha squared divided by dimensionality. So that alpha squared is a very favorable place for alpha to appear. Dividing by d is not so favorable, showing that in high dimensions, in fact, differential privacy is very stringent. It's hard to be private in all directions. Anyway, that's the kind of equation I want. There's an equation that relates a knob that's kind of come out of the computer science literature, alpha, and the statistical n and d, and relates that to the risk. So I can now control if I dial in the risk, I want 0.05 in my error rate, right? I can pick n and alpha d in a certain way to ensure that that all happens in a privacy situation. All right, so in a longer talk, I would give a bunch of examples of where this allows you to actually design privacy policies and use new mechanisms that aren't add Laplace noise to the data or whatever, that are provably optimal under this criterion. They match that rate exactly. All right, so that's one example. Let me now turn to an even briefer one that is kind of looks similar, but it's a different externality. All right, let's suppose now your resource is communication. I'm going to give you multiple processors, and you want to solve your problem as best you can using all of your multiple processors available to you, but you've got to transmit the data over a link back to the mothership so you can do the data analysis. And there's a bit rate constraint. You can't transmit terabytes or petabytes of data, so what's the best statistical analysis you can do under a bit rate constraint? All right, that's now taking communication theory and trying to put it into contact with statistics, saying, can I bring the bit rate constraint B into a statistical formula that relates all the other constants? All right, so we've worked on this, and the pictures of the thing on the left looks very similar to the privacy story. Now the data are distributed, they're M machines, and there's a channel going back to the mothership theta hat, and that channel has limited bandwidth, so you better restrict yourself by a channel, by compression, taking X into Z, and then using the compressed data to do the statistical analysis. You set up a particular loss function and problem, and you study this mathematically, and here again is a walled style formulation of this. You look at a certain risk function, you look at the minimax risk, and now you take the best possible compression scheme, that's the pi sub b, under the b bit rate constraint, and try to see if you can get out a best possible compression for solving a particular statistical instrument problem. So this is very different than a Shannon bit rate constraint for communication in general. It's for statistics problems, compressed so that you can do statistics. And so we have done this analysis in a number of problems, and here's kind of the simple vignette again is this is estimating the mean of a location parameter of a Gaussian, so d-dimensional theta. And when you do the analysis, here's the classical minimax rate. It's 1 over the total number of data, which is n data points per m machine, so n times n is the total amount of data, so it goes as d over that. There's your classical minimax rate. And when you do it in this bit rate constraint setting, you get out a new minimax rate, and where is it going to come up? All right, there it is. There's the new rate. On the right-hand side, you have the classical minimax rate multiplied by a new factor, which has the bit rate, the communication constraint in it. We're taking the minimum of D, the dimension of the problem, and B. And now the interesting thing here is that if you set B equal to D, you set your bit rate constraint to the statistical dimension of the problem. Those are unrelated ideas. But if you set them to be equal, they cancel, and you're back to the classical minimax rate. So it's actually a tie between communication theory and statistical inference, which I'm not aware of having been discovered before, but you find these things when you put these two theories into juxtaposition. Okay, so that's first two-thirds of my talk. Last third, let's turn now to the externality being computation. So these resources we've been talking about so far, privacy, communication, there's a few others. We can think of them as resources. I'm sitting on the computer trying to do statistical inference, and I'm going to trade off these resources against my other resources. Well, what about the resources such as time and space that are classically studied in computer science? Can they trade off with statistical inference? Right, now this is hard. Turing sort of started complexity theory. It's very worst case. It's machine dependent. So all the constants that come into lower bounds in computer science that aren't known, they're not so bad in computer science because you're in the computer science world. But when you try to bring it into our world, you can't make comparative statements anymore because you have all these unknown constants. So it is an ongoing, really hard problem to get lower bounds in complexity theory in general. But in this new world, it's really, really very hard. There is some work that I wanted to, on one slide, allude to that still is at this kind of polynomial versus exponential boundary, which I poo-pooed earlier on as not very important boundary. But let me just say there is interesting work going on at that boundary. Starting with a very provocative paper by Berthet and Rigolet just now 2 years ago on sparse PCA, and there's a sequence of other papers. My colleagues and I just finished a paper just before coming here this week, where you show that in the statistical setting, it's impossible to solve certain problems when you're asking for a certain error rate. You just can't do it. Okay? If you're more generous with the error rate, then you can solve the problem, but only with an exponential algorithm. And then provably, when the error rate gets less and less stringent, now you can solve the problem with polynomial algorithms. So these are the first gaps that this has kind of been an open problem to find these kind of gaps. Is the polynomial exponential boundary actually relevant to statistics? And the answer is that yes, it is. So there's now a class of problems that were sort of exotic, sparse PCA to less and less exotic over time, where this gap emerges, and then on the left-hand side, instead of undecidable, you have impossible in a statistical sense. So it is a merger of statistics and computing. All right, but it's not really for this talk, where the big data is the important issue, so exponential polynomial is not really relevant to, I think, our main issues. So what we've been doing in this domain has been really looking more about mechanisms and bounds. Can we kind of think of new mechanisms in which we can analyze them statistically? There are kind of computer science mechanisms like convex relaxations, concurrency control, oracles from optimization, and there's a whole sequence of papers that I won't be going over, where this has been the attempt. We don't have a general, beautiful Shannon-like theory of computation meets inference, but I think that will emerge over time, and this is kind of first probes into what the mechanisms would be. Just think, parallel computing already was kind of hard for Turing. If we allow ourselves to have parallelism, obviously we can drive down statistical error, but at what rate? That really becomes a very, very hard problem. So in the last 7 minutes, or less, hopefully, I just want to briefly allude to the subsampling paradigm, because for me, big data, that's kind of the first thing that comes to mind. You got this huge amount of data, the first thing you think of doing is taking a small subsample and working with that. All right? Now, naively, that seems like the solution to all your problems, but in statistics, that's just not going to work naively. Error rates, error bars, confidence intervals all have size, which depends inversely on typically the square root of the sample size. If I subsample by a factor of 10, my error bars are off by a factor of square root of 10. I'm just getting dead wrong answer. All right? And if I don't know a priori how those things are scaling, I don't know how to rescale it after the fact. Okay? All right, so if you don't think about confidence intervals, if you just think about output, point estimates, a machine learning system taking in an input, putting it on an output, if I have less data, it'll probably do just as good, maybe a little extra error, but no big deal. Sweep it under the rug. But if you're thinking about decisions and real inference, you got to get confidence intervals. The size of the error bar depends on how much data you have. So when you subsample, you have a problem. All right, so let's think about this a little bit. Now, the one way to set this up is that the risk function, instead of being a priori like in the previous part of the talk for theoretical analysis purposes, is now a posteriori. I got some data. Tell me what the risk is after you've gotten the data. What's the bias and variance? Those are a posteriori risk quantities. All right, so I have to be careful, and let's think about this for a second. So let's suppose I've received some data, I've put it through some procedure, I've got an answer theta hat, all right, and I want an estimate of the quality of theta hat. I don't care how you got theta hat, how fast you made that, and so on. I don't care what theta hat is. I care about how good theta hat is. Can you be honest about it? Even if it's bad, I want to know that, so I can say you should get more data or try some other procedure. All right, so how do you do this? Well, a statistician always thinks about the underlying population. The inferential problem involves thinking about what came behind the data, not just the data itself. All right, so there is a population that generated the data, and it could generate more. And so the picture that you can think about as kind of almost the definition of frequentism is that you have a population, and then repeatedly you got multiple data sets. Data set 1, data set 2, data set M. Right? And in parallel, you took all those data sets and put them into your procedure theta hat and got out multiple values of theta hat, and now have a notion of a fluctuation. It's called the sampling distribution. And you can put it into a formula that maybe takes an interquartile range and says, there's my error bar. That's almost the definition of an error bar. All right, so in heaven, the supreme being has the population and can do this on a cloud computer. In parallel, generate multiple data sets and get fluctuations and get an estimate and an error bar. You only have one data set here on Earth, so you can't do that diagram. But there's this beautiful idea, largely elaborated and due to Brad Efron, which said the following. You don't have the population, but you have data sampled from the population, form a histogram. That's a good estimate of the population and uniformly good. So forget that there was a sampling issue. Just treat that as the population. Your data is now thought of as the population, and sample from that instead of sampling from the population. That's the same thing as resampling the original data with replacement, which is how the bootstrap is usually explained, but it's really just plugging in for the population and histogram based on the actual data. So there's the picture of the bootstrap. It took in the data on the left instead of the population, but then sampled from that multiple times in parallel, got the fluctuations, and put them into a formula. Everything is the same as before. And if all those operations are continuous, and we were close in supremum norm on the left, and we're functionally analytically continuous, then the answer we get out is the same as up to an epsilon as what the supreme being got out. So it's a beautiful idea that just involves continuity argument. All right, now, what about big data? What if that thing on the left is petabytes or terabytes or whatever? When we resample with replacement, we get data sets of the size terabytes. Right? And we can't send hundreds of terabytes on our cloud computer and hope to, in any reasonable amount of time, get a reasonable answer. So you can't do the bootstrap on big data, sort of naively. Okay? So here, that slide sort of sets that up. All right, so last couple of slides, let me just sort of say this problem can be solved. Instead of taking the original data and resampling with replacement, you take a subsample of the data of size B. All right? Naively, the error bars based on that would be incorrect, right? But for the same reason as before, the subsample is an approximation of the population also. It's not as good an approximation, but it is. And you can pretend that that's your population. And you can resample from that object as many times as you want. Even though it's based on B data points, you can resample n times from it and get error bars on the right scale without any corrections whatsoever. So you just plug in, and here's this picture will show you how you do this. Here's a big data architecture that takes the data on the left. It's too big to work with, but you subsample it, and then in each upper box in parallel, you bootstrap the subsample. All right? You take the subsample and bootstrap it, and you get correct error bars in each one of those boxes. They're a little noisy because they were based on a possibly unrepresentative subsample, so you average the error bars. And now you can do the math that convinces you that's correct. So this kind of architecture is extremely successful in practice. This is an example of a terabyte scale logistic regression showing as the amount of time goes down, the bootstrap is the blue curve running and running and running, resampling and resampling, and after about 15,000 seconds it starts to stabilize. It starts to. The new procedure runs on, this is all on a cloud computer, Amazon EC2, runs and finishes within about, it's the red dot there, within about a couple hundred seconds and gives an answer of much higher quality than the bootstrap. So I never thought this would conceivably be possible. The bootstrap is so simple, so straightforward, it just in parallels, samples a bunch of things, but you can totally beat it. You can, totally, kick it out of the water with a procedure that takes advantage of the modern kind of distributed computing architecture and does statistical inference in a reasonable way, but also computationally reasonably. And 40 years of the bootstrap, people hadn't discovered this procedure. So there's a whole bunch of different varieties of bootstrap, but they missed this one, and it's just because they weren't thinking computationally. It was enough just to write down a statistical analysis that some procedure gave you consistency and not think about this. So I don't think there's anything special about the bootstrap, and this, I think there's going to be lots of ways when you bring computational statistics together. It's not that we're just going to be good theoreticians and protect ourselves. We're actually going to get a surprising, interesting new phenomena coming out that we would not have ever seen if we didn't think about these problems jointly together. Okay, so there's my last slide. I hope I've convinced you in my short time that there are many new conceptual and mathematical challenges in big data. It's not just a system building exercise and make things scalable by building things. That's part of it. That's great. That's what all the conferences are doing. It's a real serious mathematical problem. It is the problem for the ages. It requires bringing two lines of thought that are hundreds of years old together in new ways at the level of their foundations. So I haven't said anything about causality. That's for the rest of the conference. But I hope you're convinced that this is a kind of the important setting to be thinking about causality. It's not just that things are big in the big data world and things, so causality has to kind of just be scalable. No, it has to be just pursued as a joint enterprise. All right, thank you. A couple of minutes for questions, if there are any.
By the way, this is a great talk on reality might not be models that you've been talking about.
Well, I mean, there's lots of mechanisms we'll see in the next 2 days, matching instrumental variables and so on and so forth. Those are all algorithms, and they run in a certain amount of time, and they have certain complexity requirements, and they have certain inferential accuracies. If you don't face that and face that the time and the accuracy is part of the problem, then you'll do causal inference, which is actually delivering spurious causes just as like any other statistical problem. So yes, I think it's part and parcel. Thank you.